Our good old physics is stuck with a problem that many of us are trying to solve. And it all started with this man, Stephen Hawking.
Strange as it may sound, I have found that things can get out of black holes. Other people call this Hawking radiation. Many physicists believe that this radiation will be completely determined by what fell into the black hole. But I think the radiation will be random and will not carry any information about what fell in.
A black hole forms, then evaporates away while emitting Hawking radiation. But the information that went in doesn't seem to come out. If this idea of Hawking is correct, it challenges a fundamental rule in quantum physics. Information cannot vanish. But black holes seem to do otherwise. And this is the puzzle. So now that we've dipped our toes into this puzzle, let's try to understand it completely. To truly understand this black hole puzzle, let's first back up and try to understand what are black holes, how is physics stuck, and how it can be resolved by breaking off our horizons, quite literally. So let's dive in. Remember Einstein, the iconic physicist? His groundbreaking theory of general relativity tells us how space-time is affected by matter and vice versa. Watch this to get a better understanding of gravity. But hold on, this theory is far more vast than the everyday gravity we experience. There are exotic solutions to his equations known as black holes. Physics Nobel laureate Kip Thorne, renowned for his groundbreaking contributions to the understanding of gravity and space-time, who also served as a scientific consultant for my favorite movie, Interstellar, describes black holes as, of all the conceptions of the human mind, from unicorns to gargoyles to the hydrogen bomb, perhaps the most fantastic is the black hole. A hole in space with a definite edge over which anything can fall and nothing can escape. A hole with a gravitational field so strong that even light is caught and held in its grip. A hole that curves space and warps time. Let me show you an example of what a black hole looks like, and not just that artistic impression. Real stuff. On your left is a black hole in the language of math. It is called a Schwarzschild metric, and it describes a region of space-time called a Schwarzschild black hole. This is one of the solutions of Einstein's equations. And on your right, we have a real image taken by Event Horizon Telescope of Sagittarius A star black hole, which in my opinion is one of the greatest successes of humanity. Now let's break down black holes using everyday ideas. Think about when you throw a ball up. Gravity pulls it back down. But imagine a rocket, much faster than that ball. It easily escapes Earth's grip. Now picture this. Trying to blast off from the sun's surface on a rocket. The speed needed to do so would be way more than leaving Earth. Why? Because the sun is incredibly heavier than the Earth and has more gravitational force to pull the rocket down. Now what if this required speed becomes faster than the speed of light? Then even light could not escape. That's when a black hole forms, capturing even light itself. A hole with a gravitational field so strong that even light is caught and held in its grip. Black holes have two unusual properties, a horizon and a singularity. Let's go to the world of blackboards and chalks and understand both of these. Black holes have an edge known as the event horizon. This is an invisible surface around a black hole whose size is determined by the energy or mass of the black hole. And this horizon is a point of no return. If you cross this surface, you cannot come out, not even light can. The other property of a black hole is the singularity. This is an extremely small blob sitting at the center of the black hole where all the mass and information of the black hole resides. And between the singularity and the horizon, there is just empty, warped space and time. Hawking's big idea. Now to explain you this, let me take a super short detour to the world of quantum physics. In the quantum world, particles can pop in and out of existence anywhere in the universe. All they have to do is to be quick, conserve energy, and pop in and out in pairs. Now what Hawking imagined was, what if this happens around the event horizon of a black hole? Everything seemed clear until it wasn't. If a pair is created around the horizon, one of the particles can fall into the black hole and the other, which is outside, can escape. The particle which falls into the black hole has a net negative energy, and this falling of one particle inside causes the black hole to lose energy. So if you view the process from far away, it would seem as though black hole is losing energy and emitting radiation as particles which were left outside. This is called the Hawking radiation in honor of Stephen Hawking. Now you would think, so what? Objects lose energy and cool down every day around us. What's the fuss about black holes losing energy and cooling down? The problem is here. Remember, the horizon of a black hole was an invisible surface and had no information about what the black hole was formed with, as all the information went to the singularity and the horizon was far away. But the radiation came out from around the horizon, and thus it cannot have any information of what the black hole was formed with. And this, my friends, is the puzzle. Our friendly theory of quantum mechanics. Okay, an overstatement. It's not friendly at all. The theory of quantum mechanics guides that processes in physical world cannot lose information. This information is not like your browser history, which can be erased, but something more fundamental. It's like the knowledge of quantum states of a system, and any quantum process preserves this information. But when a black hole radiates, it shrinks and eventually disappears. The information of the stuff that went in is lost, and there seems to be no way one can retrieve it. So what's the resolution? Do we have one? Well, there are many resolutions to this paradox, but only one seems to be the most natural. But if one agrees to this resolution, they have to give up on all old understanding of a black hole and replace it with something known as a fuzzball. This resolution was provided by Samir Mathur of the Ohio State University in the late 90s. He tells that to answer any question that involves both gravity and quantum theory, one must start with a consistent theory of quantum gravity. Enter string theory. To make a black hole in string theory, one needs objects in string theory, like strings and brains. But each time one makes such a bound object, one finds that the massive object doesn't shrink to a blob of singularity. Instead, the object swells up in size and becomes a fuzzy ball of strings and brains called a fuzzball. Let us go back to the world of blackboards and chalks to see what changed. I place the old and the new picture of what one might consider a black hole. On your left is the old version of a black hole which has a singularity and a horizon. On your right, you see a fuzzball which no longer has a horizon. This mess of strings and brains come out naturally as a solution of string theory. And when one does not have a horizon, the object behaves just like a piece of coal which radiates as it cools and preserves information. The beauty of this idea lies in its simplicity, and this simple yet profound resolution marks the end of Hawking's puzzle. But then you may ask, how did astronomers take a picture of a black hole and not a fuzzball? The answer is rather straightforward. String theory suggests that fuzzball structure modifies what happens inside the black hole's horizon, successfully solving the paradox. However, the physics outside the fuzzball remains almost unchanged. This means that any image we capture would still portray the familiar silhouette of a black hole, as its gravitational pull remains exceptionally strong. Yet a significant shift occurs. The emptiness that existed between the singularity and the horizon in the traditional black hole is replaced by the intricate fuzzball structure provided by string theory. So what lies ahead? Are we done? There are numerous interesting questions awaiting exploration. Firstly, a deeper understanding of how stars die and evolve into fuzzballs rather than black holes. Could fuzzballs potentially offer solutions to other cosmic puzzles? such as the Big Bang and the Hubble tension? Additionally, how might we experimentally confirm the internal structure of a fuzzball? While these questions pose tremendous challenges, they echo the sentiment of Stephen Hawking's words. If you feel you're in a black hole, don't give up. There is a way out. Thanks for watching. I hope you liked this video on the black hole information paradox, and I hope that you got inspired with Hawking's words of inspiration. Don't forget to like, share, subscribe, and hit the notification bell button for more similar content. Until next time, signing off, your host Madhur. Keep exploring and stay curious.